A system goes through the following three-step process. Pretty classic question, some energy transfers. What I recommend doing for this type of question is draw yourself a little box to act as a system. Okay, so I'm going to make myself a system. Ooh, ah. Then draw the arrows accordingly. If energy is going into the system, the sign of the energy transfer is positive. If it's going out of the system, then it's negative. So let's go through and do a little documentation station here. The system absorbs 25 kilojoules of heat from the surroundings. Okay, so if it's absorbing, what I'm going to do is process 1 is plus 25 kilojoules. Okay, and then I'm just going to put a little check here. We've taken account of that. Process 2, the system performs 10 kilojoules of work on the surroundings. Probably the most, well, a familiar way of visualizing performing work is if ice expands on sidewalks, especially here in Pennsylvania, we have this all over the place. When it expands and causes cracks, that's doing work on the surroundings. So expansion is doing work. And if it's doing work, the arrow points outside of the system, and the sign would be what? Positive or negative? Negative. Negative 10 kilojoules. And then finally, check. Then finally, the system transfers 20 kilojoules of heat to the surroundings. Okay, so you have another arrow facing out, and it's going to be negative 10 kilojoules. So the overall delta E of this is going to equal 25 kilojoules plus negative 10 kilojoules plus negative 20 kilojoules, which equals negative 5 kilojoules total. Our choice, C. Okay. 1 down, 29 to go. Let's do this. The next question, the following quantum numbers describe 5 electrons in the same atom. Which set of quantum numbers describes the electron with the lowest energy? The most important quantum number in determining energy is the principal quantum number n, how far away the electrons are from the core. So first we want to look for the lowest principal quantum number n. And that means we can actually eliminate 3 different choices. We can eliminate B, D, and E. Okay? Halfway done. Now, the next one is going to be L. Because S is lower in energy than P, which is lower in energy, D, which is lower in energy than F. This corresponds to L equals 0, 1, 2, and 3. So the answer is going to be C. Okay. This is the 2s subshell. It is closest to the nucleus. The closest it is to the nucleus, the closer it is to the nucleus, the lower the energy is going to be, the more stabilized our electrons are going to get. Okay. All right. Up next, which of the following transitions in a hydrogen atom will emit a photon of the greatest energy? To do a problem like this, I like to draw a little diagram. The diagram looks a little something like this. We have our n equals 1 state is the lowest energy state. And what we're doing is just showing these in order from lowest energy to highest energy. I'm going to do a really, really exaggerated jump then to n equals 2. Then slightly less exaggerated jump to n equals 3, then n equals 4, then n equals 5, and it starts to get really, really smushed together. The key idea behind the Bohr model is the energy gap from 1 to 2 is greater than the energy gap from 2 to infinity. The energy gap from 2 to 3 is greater than the energy gap from 3 to infinity. The energy gap from 4 to 5 is greater than the energy gap from 5 to, et cetera, et cetera, et cetera. It gets exponentially smaller with each step we make, which means any transition involving n equals 1 is going to involve the greatest amount of energy, okay? Since it says emission here, are we going from lower to higher or higher to lower? Higher to lower. This is sometimes a way of eliminating some answer choices. In this case, they're all higher to lower, but so the answer is going to be A, because this energy gap from 2 to 1 is greater than the energy gap from 6 to 2 and from 10, which is not pictured, to 3. 2 to 1 is bigger than the rest of the graph, okay? You technically could use the Rydberg equation to calculate these, but it's not necessary. These types of problems can always be solved with this sort of approach. All right. Which of the following describes the correct number of protons, neutrons, and electrons in potassium? Okay. So we're looking at potassium 40. Potassium is element number 19. So I'm going to put a 19 subscript there. And specifically, I should warn you, there's going to be some tacky chemistry jokes. Those of you in my section, sorry you have to hear them. I'm not sorry, but you will have to hear them again. We're specifically looking at a potassium cation. You can remember cation because a cation is positive. Like cats, they got pwas. Cations are positive. It's a great mnemonic. Okay, and let me pull up the periodic table just for your reference. If you look at the periodic table, well, I'll just draw a little periodic table here. Potassium is found right here. It's element number 19, which means it has how many protons? 19. So okay. Here's potassium. Whatever the element number is, that's the number of protons. So it's got 19 protons. Then the number of neutrons is going to be equal to the number of nucleons minus the number of protons. The number of nucleons is this value up here. That's the protons plus the neutrons. So the number of neutrons is going to be 40 minus 19, which is 21. And then finally, if it's a cation, positive, is it going to have more or fewer electrons than protons? Fewer. The protons are going to outnumber the number of electrons. In this case, since the charge is positive 1, that means we're going to have 1 fewer electron than protons, so 18 electrons. So 19, 21, and 18, which means our answer is C. Which set of quantum numbers is not permitted? All right, so the rules for quantum numbers. N can be any positive integer. 1, 2, 3, dot, 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 et cetera, et cetera, et cetera. L, the azimuthal quantum number, is limited by the value of n. It goes from 0 up through n minus 1. It can never be equal to n or exceed n. And then m sub L is equal to negative L to positive L. Finally, m sub s can equal either positive 1/2 or negative 1/2, upspin or downspin. So looking through these answer choices, A, n equals 2, that's cool. If n equals 2, can L equal 0? Heck yes, it can. If L equals 0, negative 0 to positive 0 just includes 0. Negative 1/2, cool. For B, 3, okay, can L equal 1? Yep. Then negative 1 to positive 1 includes that. Okay, that's fine. So most of these are fine until we get down to E. E, if n equals 3, is there any way L can equal 4? No. I should think not. This one is not permissible. Okay, L cannot be equal to or greater than n, and that's what makes this one wacky, or sus, as some would say. Okay. All right. How many degenerate orbitals are there in the n equals 3 shell of the hydrogen atom? Now, it's important to note that hydrogen is different from every other element. Hydrogen is very simple. There are no shielding electrons to change the energy levels of the subshells. What this means is, if n equals 1, there's only one subshell. That's where L equals 0, and that is the 1s subshell, which has one orbital. If n equals 2, higher in energy, there exists a 2s subshell, but this also opens up not just 2s, but 2p. And how many orbitals are there in a p subshell? 3. Okay. Now, if n equals 3, we have a whole new world full of orbitals. We have 3s, we have 3p, and we also have what? 3d. And how many orbitals are there in a d subshell? 5. Okay. 3s, 3p, and then 3d. Okay. And all of these are in terms of energy going up. With hydrogen, the only number that matters for energy is the principal quantum number n, which means all 3 of these subshells are equal. And we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 total. Okay. So hydrogen would have 9 degenerate orbitals in the n equals 3 shell. Yes. If the question said good question. If the question said non-hydrogen, it would need to specify the subshell then, because subshells in every other atom are degenerate. In hydrogen, it's shells, in other ones, so we would have to give you more information. Okay? Good question. All right. Oh, yeah. Good question. The question was, how can it have 3 shells if it only has 1 electron? That electron usually lives in the ground state, the lowest energy state. But if we add energy to it, it can be kicked up to a further away orbit. So they do exist, they're just not heavily utilized. Okay? So they are there, but if we wanted to put an electron in one of those orbitals, we would have to excite the electron and move it up to a higher energy state. Yes, the question was, can you have as many shells as you want? And yes, theoretically, any atom can have an infinite number of shells. In practice, an infinite number of shells aren't used. Generally speaking, shells range from 1 to 7, n equals 1 to 7, but theoretically speaking, they exist 8 through infinity as well. All right. And then the 7th question says, how many kilograms are in 126 micrograms? This is a dimensional analysis problem. And what we're going to do is, there are a few right ways you can go about doing this. What I recommend doing just to be safe is convert from micrograms to grams. In 1 microgram, what does micro mean? It means 1 times 10 to the negative 6th. So there's 1 times 10 to the negative 6th grams. We're not done yet. We want to convert to kilograms. So ultimately, we want to cancel out grams now. And in 1 kilogram, kilo means 10 to the 3rd. And then when we do all this, micrograms cancels out, grams cancels out. And then when you multiply 126 times 1 times 10 to the negative 6th, and then divide by 1 times 10 to the 3rd, you get C. Or sorry, D. Oh, there is no D. You get B. 1.26 times 10 to, no, yes, the negative 7th. Okay. I just want to note, as you prepare for the first exam, just make sure you're comfortable with how your calculator does order of operations, okay? So if you were to type this in as 126 times 1 times 10 to the negative 6th, it treats it differently than if you put things in parentheses. Personally, my favorite calculator to use quick little calculator life hack. Okay, my favorite calculator to use is the TI 32X, or excuse me, 30X2S. And I want to point out, this has a very useful button that's often underutilized. The second E is really, really useful. The E just means times 10 to the. So when doing this calculation here, I can take 126. Micro means times 10 to the negative 6th. So all I have to do is type in second E, negative 6, and that automatically puts it into the appropriate form here. Then I divide by 1 times 10 to the 3rd to turn it from kilograms, or from grams into kilograms. And then you can switch into scientific notation, and hence, and hence. And voila, we have our answer. Okay. So just general recommendation, make sure that you're well acquainted with the functions and features of your calculator. Okay. Up next. I also want to note, how do we feel about these questions so far? All of these questions are classic exam 1 questions and are quite represented on the actual exam itself. So if you're feeling good so far, that's good. That's very good. Yes. It does. The other beautiful thing about the E function is it prioritizes it in order of operations. It makes sure that that times 10 to the whatever is attached to the number that it follows. It's a fantastic operator. All right. A microwave uses electromagnetic waves with a frequency of 2.45 times 10 to the 9th seconds to the -1 or hertz to heat food. All right. Oftentimes in chemistry exams, one of the best strategies is Think about what you're given, think about what you're trying to find, and then think about what equation or concept relates the two. In this case, we're trying to relate frequency, which is nu, or a letter V, and we're trying to relate it to wavelength. And wavelength is lambda. By writing things like this down, you can look at your data table and you'll see that the equation that relates these two is the speed of light is equal to wavelength times frequency. Plugging in our values, the speed of light is 3.00 times 10 to the 8th meters per second is equal to lambda, which is what we're solving for, times the frequency, which is 2.45 times 10 to the 9th seconds to the negative 1, or hertz. We'll divide both sides by frequency. Seconds will cancel out, and we'll get that lambda is equal to 0.122 meters. Okay, but we're not done yet. The question says in centimeters. So there's a quick little dimensional analysis then. For every 1 centimeter, there's 1 times 10 to the negative 2 meters. And then this will end up equaling 12.2 cm. Right. Up next, below are 2 orbitals of the 4th shell of an atom. How do their quantum numbers differ? By virtue of being the 4th shell, it means n equals 4. Anything in the 4th shell, the shell describes the principal quantum number n. Also, these are both the same genre of subshell, or of orbital. These are both d orbitals. They're just different d orbitals. By virtue of being d orbitals, they have to be in the L equals 2 subshell. Okay? L equals 2 means you're looking at a d orbital. So both n and L are the same. The only difference is the actual individual orbitals themselves, which is m sub L. So the answer is A, the same n and L, but different values of m sub L. The 4 shapes that you want to be familiar with are spherical is S, dumbbell shaped is P, and then clover shaped and dumbbell with a donut around it. These are both D. As long as you know those shapes, you're good. Okay, which of the following diagrams below is a valid representation of an excited state of O+ ion? There's a few different ways to go about doing this problem. What I would do first is, I would calculate the number of valence electrons, or the number of electrons total in this. Yeah. What? You do not need to know what an f orbital looks like. They're too bizarre in shape. So do not worry about the f orbitals. Okay. All right. So to go about this problem, first, I would find the electron configuration of a regular old ground state O+. Oxygen is element number 8. So regular old oxygen has an electron configuration. We can start from the top left and work our way down to here. This is the S zone, so it's 1s2. Then we work our way down to the second period, 2s2, and then 2p, 1, 2, 3, 4. So for the ground state, oxygen would be 1s2, 2s2, 2p4. But if we're making it O+, we're removing an electron. And we remove it, generally speaking, from the highest energy orbital. So to make it 1s or O+, it would be 1s2, 2s2, 2p3. So the ground state electron configuration would be 1s2, 2s2, 2p3. This has a total of 1, 2, 3, 4, 5, 6, 7 of 7 electrons. We can eliminate any answer choice that does not have 7 electrons. So looking at these different answer choices here, A has 1, 2, 3, 4, 5, 6, 7, 8 electrons. And we can get rid of it. B has an impossible electron configuration. This cannot be done. For an excited state, you can violate Aufbau principle, you can violate Hund's rule, but you can never, ever, 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 ever have 2 ups or 2 downs in the same orbital. Just can't happen. Yuck, ooh, forget about it. Then between C, D, and E, C has 1, 2, 3, 4, 5, 6 electrons. That's not right. And then between D and E, we've got 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3, 4, 5, 6, 7. These both have 7 electrons. We're specifically looking for an excited state. Between these two, D has the excited state. There's 2 things that are excited. There's this electron here is flipped, and we have an electron that's jumped up to a higher energy orbital. E is incorrect because this is the ground state of O+. Okay, yes. It is possible. An excited state, there's always one ground state, or at least it doesn't matter which orbital you start filling out because they're degenerate, they're equal in energy. But an excited state can be any rearrangement of electrons. You could take something from the 1s and promote it all the way up to the 7p if you wanted to. That would be an example of an excited state. Okay. Okay. Excited. Up next, 11. Shown below is the ground state valence electron configuration of an element. Identify the element. All right, so it's 4s2, 3d5. So 1, 2, 3, 4. This is the 4s. This is the 3d block. Just for posterity's sake, I'm going to include that the core is argon. We don't need to include that here, but why not? And then 4s, 1, 2, 3d, 1, 2, 3, 4, 5. We're looking at manganese. Choice B. Okay. All of the electron configurations that you're responsible for follow this pattern where you can count across. Let's say we were looking at arsenic. You would go argon core and then 4s, 1, 2, 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then this is 4p, 1, 2, 3. So by doing this counting, you can always find the electron configuration on a given atom. There's only 2 exceptions that you're responsible for. Those are chromium, which is right here, and copper. The reason for the exceptions is the D subshell, it turns out, is kind of greedy. If it can be half filled or fully filled, it's going to yoink, borrow an electron from the 4s and As a result, chromium is 4s1 3d5, copper is 4s1 3d10. All right. Arrange the following in terms of increasing first ionization energy. The trend for first ionization energy is as follows. As you work your way across the periodic table in a given row, there's more protons. The more protons you have, the harder it's going to be to pull an electron away because it's more attracted to the nucleus. So first ionization energy always goes up as you go across the periodic table. It's really easy to remove electrons from the metals. It's really difficult to remove them from halogens and things on the right-hand side. Additionally, what is going to be easier to pluck an electron away from? An electron that's close to a nucleus or an electron that's further away? Further away. The further away it is, the less attracted it is to the nucleus. And as we work our way down the periodic table, atoms get bigger and bigger and bigger. So francium is the easiest one to pluck an electron away from, and it gets more and more difficult as you go up and to the right. So the trend here is first ionization energy increases as you go up and to the right. With this particular example, we have barium and strontium, and then tin and germanium, which are right in here. So we've got germanium is right here, and tin is right below it. Oops. So it's going to be barium has the lowest, then strontium, then tin, then germanium. Or choice A. There will always be a logical way of putting these in order. We would not give you one where you have to compare, say, silicon and arsenic, where they're off the diagonal like that. So there'll always be a logical way of putting these in the correct order for any trend question. Yes. You are, yep. So on the exam, you'll be given a periodic table, a data table, and a piece of scratch paper. You're welcome to write whatever you'd like on them. The energy change of which of the following reactions defines the electron affinity of element X? Choice E. Electron affinity is adding an electron to the neutral element in its gaseous state. And when you add an electron to something, a neutral element, you're going to turn it into its anion with a negative charge. Okay. So by definition, electron affinity is an atom as a gas plus an electron yields the -1 charge. The following image shows a series of isoelectronic ions and their ionic radii. Which of the following ions has the largest atomic number? Isoelectronic means equal number of electrons. So if all of these have the same exact electron cloud floating around them, why is it that the furthest one is the smallest and the one on the left is the largest? What can pull those electrons in closer and closer and closer and closer and closer to the nucleus? Yes. The nuclear charge. The more protons we have, the closer they're going to be pulled in to the nucleus. So the smallest has the most protons. The largest has the fewest protons. And the more protons you have, the greater the atomic number is. So it's choice E. Okay. Question 15. The mass spectrum of atom X is shown below. What can be surmised about the average atomic mass of X? You don't need to do any calculations on this problem. You can do calculations. That works perfectly fine too. We have a majority of the element is 160. 28.3% is 158, and then 162 is 20.3. So the most represented isotope is 160, but which way is the atomic weight going to be more skewed toward? The one that comes in second place or the one that comes in third place? It's going to be more skewed toward the one we have more of. So while it is close to 160, it's going to be just south of that value. To show the calculation, though, atomic weight is equal to the sum of the mass of the isotope times the isotope abundance. And in this case, it would be equal to 158 AMU times 0.283 for this one, plus 160 AMU times 0.514 for this one, plus 162 times 0.203. This is also AMU. And this ends up equaling 159.84. So you absolutely can do the math, but you could also, by looking at which ones are more represented, you could also come up with an estimate instead. Which of the following is not a common ion of the main group element, This involves the octet rule. Elements tend to gain or lose electrons to have 8 valence electrons. And if you look at metals, so the first one, let's jump down to potassium. Look at this first. With potassium, it has 1 valence electron. The valence electrons are equal to the group number. So 1, 2, then over here, this is 3, 4, 5, 6, 7, 8. Is it going to be easier for potassium to gain 7 more electrons, or to just take that 1 lone electron and drop it as if it's hot? Drop it as if it's hot. It's going to be much easier to just lose that 1 electron. So potassium tends to have a positive 1 charge. In fact, anything in group 1 tends to be positive 1. Anything in group 2 tends to be positive 2. So potassium plus 1, that's perfectly fine. Magnesium. Magnesium is right here. It's group 2. Easier to gain 6 or easier to lose 2. Easier to lose 2. This one's fine as well. Going to the other side of the periodic table, looking at fluorine. Fluorine has 7 valence electrons. Is it going to be easier for it to lose all 7 of them or just gain 1 more? Gain 1 more. So fluorine will tend to gain an electron to become F minus. Sulfur, which is right here, has 6 valence electrons. What do we think? What's it going to do to get to 8? It's going to gain 2 more to become 2 minus. The only one that does not work here is chromium. Chromium is a little bit finicky. Transition metals are slightly funky with what they do, but chromium has 6 valence electrons. It's got 2 from the 4s, and then the 3d is 1, 2, 3, 4, it would not tend to lose just one electron. That would not give it an octet. And truth be told, transition metals can have a variety of different charges. You're not responsible for knowing them. But in this case, we can eliminate all of these other answer choices. So these are all common charges, and this would not satisfy the octet rule. Question 17. An average apple has 12.6 grams of fructose, C6H12O6. How many oxygen atoms are in this? This is a classic dimensional analysis problem. And our goal is to keep converting units until we get to what we want. So it's 12.6 grams of C6H12O6. In order to get to the number of atoms, we need to use the universal currency of chemistry, which is the what? The mole, okay? Moles are oftentimes central conversion factors in these types of problems. And in order to convert this to moles, what we need to do is, looking at C6H12O6, to find the molar mass, we're going to look at the weight on the periodic table. Truth be told, with these, you can just round their mass. You don't need to do like 12.011. Generally speaking, 3 working digits works pretty well in this course. But carbon weighs about 12 grams per mole. If you look at the weight, oxygen weighs 16, and hydrogen weighs a cool 1. So carbon is 12 grams per mole, and there's 6 of them. Hydrogen is 1 gram per mole, and there are 12 of them. And oxygen is 16 grams per mole, and there are 6 of them. This equals 180 grams per mole. And that's going to be our conversion factor. So to go from grams to moles, you divide by the molar weight. 180 grams of C6H12O6 for every 1 mole of C6H12O6. But are we trying to find the number of moles here? Nay, we're trying to find the number of oxygen atoms. There's 2 different ways we can go about. They're going to involve the same exact calculations, though. What I like to do first is, for every 1 mole of C6H12O6, a mole always means the same amount. Like a dozen. If you have a dozen cookies, that means 12 cookies. If you have a dozen donuts, that means 12 donuts. If you have a dozen ribeyes, that means 12 ribeyes. A mole always means Avogadro's number of something, which is 6.02 times 10 to the 23rd. Right? So it's 6.02 times 10 to the 23rd C6H12O6 molecules. If the question asks how many molecules, we'd be done, but it specifically wants to know the number of oxygen atoms in this. So then finally, for every one C6H12O6, there are how many atoms? For every molecule, how many oxygen atoms are there? 6. There's 6 oxygen atoms. And then when we do this, grams cancels out, moles cancels out, molecules cancels out, and we're left with oxygen atoms. This ends up equaling 2.53 times 10 to the 23rd. Oxygen atoms. Ready? Yes. Mm-hmm. Yeah, so for this one, this is on your data sheet as n sub a, and it has a ridiculous number of digits in it. For Avogadro's number, I can't think of a time where using 6.02 times 10 to the 23rd hasn't worked. So 3 working digits will do you just fine. Okay. So again, if you have a mole of something, it's always Avogadro's number, 6.02 times 10 to the 23rd of it. Which reminds me, can anybody tell me how many moles there are? Or sorry, how many, take a step back here. How many guacs are present in a mole of guacamole? Avocado's number. Thank you, thank you. You don't have to applaud that. It just felt like it was time for a bad science joke. Okay. Which of the following statements about metals and nonmetals is true? On the periodic table, we have our metals over here. We have our nonmetals over here. And then we have metalloids, which are kind of not quite metals, not quite nonmetals along the stair step. All right, most of the periodic table are metals. So all of these are metals. These are nonmetals. These ones are kind of iffy. All right, let's go through these statements. Nonmetals are good conductors of electricity because little energy is required to remove valence electrons. Now, there's a few things that are a little sus here. First of all, nonmetals, good conductors? I don't think so. In our general experience, what type of materials conduct well? Metals. Metals conduct well. Nonmetals, not so much. But it says a little energy is required to remove the valence electron. Have you tried taking a valence electron from fluorine? It's pretty tough. Oh yeah, if you had like little microscopic tweezers and try to pull one away. It's very difficult to remove electrons from this side. They would rather gain electrons. So statement A is false. B, metals tend to accept electrons to form stable anions. Nope. Metals have fewer valence electrons. They tend to lose electrons to form cations. You will never, ever, ever, ever see a negatively charged metal in this class. They will only be neutral or positive. All nonmetals are extremely reactive, losing electrons to form positive anions. So the moniker all here makes it a little suspicious. All nonmetals are extremely reactive, losing electrons to form. Well, fluorine is a nonmetal, and it's not going to lose electrons to become F+. So likewise, you're never going to see F+ in this class, or really, for all intents and purposes, ever. Okay? So nonmetals tend to actually gain electrons or be stable just as they are. Carbon is plenty stable as it is. D, metals are found on the lower left side, nonmetals are on the upper right. Hey, that one's good. We have our answer. And then metal and nonmetal ions cannot be isoelectronic. That's not true. A metal can lose an electron, a nonmetal can gain an electron, and they can have the same number of electrons total. The plot at the right shows the first 5 ionization energies of an element. Which of the following elements is most likely candidate for this element? Okay. Now, with this type of graph, what it's showing us is the energy it takes to remove the first electron, second electron, third electron, fourth, and fifth. And the first one, it's not so bad. The second one, the third one, okay, it's getting harder and harder. It'll always get more difficult. But then something wild happens. Between 3 and 4, whoa, look at that spike. It's a pretty notable jump in energy. Why is the energy spiking so much? Why does it take so much more energy to remove that fourth electron than it takes to remove the third one? You both are correct. So yes, sorry, it was kind of very vague with my pointing. Yes, you were both correct. What is happening here is these first 3 electrons are valence electrons. They're on the outside. Once the first 3 are removed, we have noble gas configuration and it's really stable. But we have this massive spike here because these 2 electrons are core electrons. And a really good rule of thumb in chemistry is we can add or subtract valence electrons. We are not going to mess with core electrons. They're too close to the nucleus. They're too stabilized. It's very difficult to remove them. And if you try to remove one, it's just going to pull an electron away from something else anyway. These ones are valence electrons. So for a problem like this, all you have to do is look for the spike. We have 3 valence, and then the rest are core. Since we have 3 valence electrons, what we do then is consult our periodic table of the elements. And the group number is equal to the number of valence electrons. So we're looking for something in group 3, and that is going to be aluminum. Let me redraw this. Right. So aluminum is right here. It's got 3 valence electrons, and we're done. Okay. Please rank the following electrostatic interactions between 2-point charges in order from lowest to highest electrostatic potential energy. With electrostatic potential energy, opposites attract each other, like charges repel each other. A rule that works well in chemistry in general is chemicals like to be chill. Lower energy is more stable than higher energy. A quick analogy. What is going to be more stable? Imagine a kindergarten classroom at 2 very different times. Time 1, nap time. Everybody's asleep and resting. Time 2, Red Bull time, when the teacher makes the egregious error of giving every kid a 24-ounce Red Bull. I don't even know if that's legal. Which one is going to be more stable, nap time or Red Bull time? Nap time. Molecules, chemicals, they're the same way. Lower energy is stable, higher energy, anti-stable. Opposite charges are attracted to each other and create a more negative energy. Like charges create a higher energy. With this problem, you can actually answer it qualitatively without doing calculations. The way you would do that is looking at these are the 2 opposite charged ones. This is going to be most negative. Between the 2 of these, the closer you get those 2 like charges together, the more repulsive the interaction is going to be. So the closer they are, the higher energy it's going to get, which means this will be the highest energy, lowest, highest, middle. If they were different charges, or if the distances were a little bit less user-friendly, the way that we could answer this is using Coulomb's law. Electrostatic potential energy is equal to a proportionation constant, K, times the charge on point charge 1 times the charge on point charge 2, all divided by D, the distance between the 2, or technically R. There we go. So doing calculations for these, R is on the bottom because that's just as you bring them closer, the denominator gets smaller and smaller, which means the magnitude of the electrostatic potential energy gets higher. R and D are technically the same thing. I believe the way it's presented on the data sheet is R. R acts as the distance between the two, but they're synonymous here, okay? And what I'm going to do then is I'm going to plug in for system 1, it's going to be equal to, the energy is equal to K, and then we've got +1 times -1 all over D. This ends up equaling -K over D. For system 2, it's K times -1 times -1 all over, keep doing that, sorry. The distance D. This is going to equal +1 K over D. And then system 3 is in the middle. It's K -1 times -1 over 2D. So -1 times -1 is 1, divided by 2 is 1/2. This is equal to +1/2 K over D. You don't actually need values to solve this problem. You can just put them all in terms of K over D. And then when comparing them, -K over D is the lowest, +1/2 is next, and then +1 K over D is the highest. So it's 1, then 3, then 2. Again, these ones have attraction. These two are repulsion. And the closer they are, the more high energy it gets. Okay. All right. A cross-section of an atomic orbital is shown below. If the number of nodal surfaces in any orbital is n-1, what is the number, or what is the orbital displayed? Okay. First of all, we've got this kind of circular spherical arrangement. What type or what letter would go with that? S. So this is most assuredly an S orbital. And then it tells us that the number of nodes is n-1. And we've got one node here and one node here. So there's 2 nodes total. And since 2 nodes is equal to n-1, add 1 to both sides, that means that n equals 3. So this is the 3s subshell. Yes. Oftentimes, clues like this that aren't necessarily as emphasized in class are given. We try to make sure that all the questions hit like high yield things, but sometimes there is the occasional like, hey, just as a reminder. Maybe, maybe not is technically covered, but we like to. I also want to note really quickly, this is a real exam. This was the fall 2019 exam. All of the practice exams are adapted from actual exams. So you'll notice certain questions seem to appear multiple times. In fact, a lot of them. There's like only so many different genres of questions here. Again, if you feel comfortable with this stuff, you should do very well on the actual thing itself. Okay, yes. Yes, absolutely. The way that we get the 3 is the number of nodes is equal to the principal quantum number -1. And what this means is if there are 0 nodes, that means that you're looking at n equals 1. Okay, so if n equals 1, the number of nodes will be equal to 1 minus 1, which is 0, using this equation here. If n equals 2, then the number of nodes are going to be equal to 2 minus 1, which is 1. If n equals 3, it's going to be equal to 3 minus 1, which is 2. If n equals 4, it'll be 4 minus 1, which is 3. This rule actually holds true for any given subshell. The number of nodes will always be equal to the principal quantum number minus 1. And so what you can always do is set up this relationship here. Nodes is equal to n minus 1, and we add 1 to both sides. That's where we got that from. Yeah. Yes, a node is an area of no electron density. A node is where no electrons dare to go. Okay, so it's represented as a blank area, an area with 0 electron density here. Okay. Yes. In terms of counting, that actually would work as well here, because with S, there's the number of layers that you get is equal to the principal quantum number. So with S, that would work. With P and with D, there's different types of nodes. There's angular nodes. And so it probably wouldn't work as well there. But with this, yes, you could do that. OK. Which of the following atoms or ions has the largest number of unpaired electrons? All right. This one is a little bit of a longer problem because calculating the number of unpaired electrons for each of these takes a little bit of time. What I'm going to do first is write the electron configuration of each of these. Fluorine has a helium core, then it's 2s2, 2p5. 1, 2, and then p, 1, 2, 3, 4, 5. Nitrogen has a helium core, and it's 2s2, 2p3. S2 minus, sulfur by itself has a neon core, and then it's 2s2, 2p, 1, 2, 3, 4. But since it has a 2 minus charge, we're adding in 2 extra electrons to it. So rather than being 2p4, it's going to be 2p6. Magnesium has, so magnesium is right here. It has a neon core, and that's 3s2. But magnesium 2 plus is going to lose both of its electrons. So it's going to be 3s0. Oh, sorry. With sulfur, I put the wrong principal quantum number. 3s2, 3p6. Okay. And then with nickel 2 plus, nickel is right here. Nickel has an argon core, and it's 4s2, 3d, 1, 2, 3, 4, 5, 6, 7, 8. With this one, I'm actually going to draw this out just to show how we would do this. So nickel by itself is argon 4s2, 3d8. And then to make it 2 plus, it turns out, I like to think of electrons as being like berries on a very delicious but very thorny bush. Where is it going to be easier to pluck the berries from? From further inside, Thorntown, or from further outside? Outside. When removing electrons from a transition metal, you always remove the s electrons first because they're further out. So we're going to take away both of these. And we're just going to have 3d8 for nickel 2 plus. Now then, I'm going to draw out 3 of these electron configurations. Anything in noble gas configuration will never have unpaired electrons. All things with noble gas configuration, by definition, have to have all completely paired. Anything with an octet, all those electrons, all 8, are going to be paired up. Okay. which means we can eliminate a few of the choices, S2 minus and Mg2 plus. S2 minus actually is, if we look at S2 minus, it actually has argon's configuration. The other thing to note is all core electrons are always paired. In the ground state. So you don't actually have to look at any of the core electrons here. Now then, let's do some diagrams. I really think diagrams are the best way of mastering quantum numbers. With fluorine, it's got a 2s subshell. How many orbitals can fit in a 2s? An s subshell can fit 2 electrons, which means it only has 1 orbital. And then it has a 2p subshell. And p subshells have 3 orbitals. Okay? S has 1, p has 3, d has 5, f has 7. If you ever forget how many electrons fit in a given subshell, look at the periodic table. And remember that periodic table is broken into zones. Just like Beaver Stadium, the periodic table has an S zone. It's got the P zone here, it's got the D zone here, and then the F block is usually not included on the actual, just because it stretches it out. But to remember the number of electrons that fit in each subshell, what you can always do is just count how many columns wide each block is. So the S zone is this. It is 1, 2 blocks wide. It fits 2 electrons. The P zone is 1, 2, 3, 4, 5, 6 columns wide. It fits 6 electrons, so 3 orbitals. The D zone is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons would take how many orbitals? 5. And then finally, F is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Wait. The F zone, I got too excited. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And the reason why the LU is up there, this one's kind of written in a funny fashion. Let me. This element here, this table is a little bit different from the one that we actually give on outer. Okay. This table is different from the one that we actually give you on your data table. What it actually did was include these two, which are in the D block, as part of this, because they're cut off. They belong here and here. Okay, so that's why it looks like 15, but it's actually 14. And the one on your periodic table has 14. Okay, all right. Okay, so with fluorine, we've got 2 s electrons and then 2 p5. Hund's rule tells us that 1, 2, 3. When we first fill out electrons, we're going to do them 1 orbital at a time before we pair them up. 4, 5. So there's only 1 unpaired electron in this one. With N, one S2, 2p, 1, 2, 3. Common misconception is that you always start with up arrows. You don't. You can go up or down. They just have to be consistent with them. This one has 3 unpaired electrons. And will actually end up being our answer. And then finally, nickel. In the d subshell, there are 5 orbitals, 1, 2, 3, 4, 5, 6, 7, 8. This one only has 1, 2 unpaired electrons. So the answer is B, nitrogen with 3 unpaired. Are there any questions about that one? It was a little bit longer of a problem. Yes. Okay, so if you had something like 3D2, all of the electrons as you start adding them in are technically unpaired. Once you start adding in like the second one into each orbital, that's when they start getting paired. So if you had like 3D5, that would be the answer here because it'd be 1, 2, 3, 4, 5 unpaired electrons. But with this one, nickel, because it had 3 more that we had to put in, it ended up pairing with 3 of them and only leaving 2 unpaired. An example or an analogy that I like with electrons that works pretty well for a lot of things that orbitals do. Orbitals are a lot like dorms, and most dorms can fit how many students? 2. If you had 3 dorms right next to each other and you had 3 students, what's probably going to happen? Are they going to like all cram into one, or are they going to each take their own space? Yeah, everybody's probably going to take their own room. But if you have 4, one of them needs to pair up. If you have 5, you would need to pair up 2, et cetera, et cetera, et cetera. Okay, got a question? It is easier to remove a p electron in a given row than a d electron. The d block starts to do funny things. Once you add enough protons, they start to actually act more like core electrons than valence electrons, but you're not responsible for that in this course. But if you had something like germanium, or sorry, gallium, Ga, which is 4s to 3d10 4p1, you would remove the 4p electron first, then the 4s electrons. The d electrons are always going to be the last ones to go. Yeah. Correct. Yep. So with gallium, you remove the p electron first and then the s electrons. And gallium actually doesn't tend to lose any of the d. Really, anything in the p block really won't lose any of its d electrons, especially nothing that we look at. All right. For the process listed, which statement is true? The enthalpy, we're going from higher to lower, which means this is an exothermic process. Can we create or destroy energy? No. So if we're going from higher to lower, that means energy is given off. In this case, in the form of heat. An example would be like a hydrogen balloon explosion. It explodes, the chemicals come down in energy, and heat is given off. So which of these is true? The system absorbs heat? No, it loses heat. The process from A to B is endothermic? No, it's exothermic. C, heat flows into the surroundings. That one is true. Yes. I'm sorry? Yes, enthalpy change is always with respect to the system. Okay, so if the system is losing, it's exothermic. If the system is gaining, it's absorbing in heat. The graph below represents the periodic trends in atomic radii. Identify atoms that are indicated by the arrows. What's going on with these graphs? With radii, as you go across the periodic table, elements get smaller and smaller because there are more protons pooling in the electron cloud. But then, once you get to the noble gas, you'll notice that we have this massive spike. The reason why we have these spikes is because atoms are a lot like onions, or they're a lot like parfaits. They have layers. And when you work your way down to the next row, you add a whole new layer to your atom. So we add a layer, and then it gets smaller. Then we add a layer, and then it gets smaller. Then we add a layer, and it gets smaller. The transition metal does weird things, add a layer, et cetera. What this means is if you ever see a graph like this, these highest points up here represent the start of a new row, okay? So we have helium down here, which is labeled. And then after helium, we have lithium is right here. We have sodium is here. We have potassium is right here, et cetera, et cetera, et cetera. These all represent the noble gases. So this one would be neon. This one would be argon. This one would be krypton, et cetera, et cetera, et cetera. Okay. So arrow 1 represents argon. And then after argon, we spike up. And then arrow 2 represents calcium. Right. So choice E. You could also, technically speaking, just count with this one. So element 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 is argon. 19, 20 is calcium. That works here too. All right. Which one of the following elements contains valence electrons that experience the greatest effective nuclear charge? Potassium, copper, or selenium. These are all in the same row of the periodic table. Potassium is here, copper is here, selenium is here. So they all have the same number of shells, but selenium has the greatest number of protons, it has the most positive nucleus. So selenium is going to experience the greatest effective nuclear charge by virtue of having the most protons. Okay, 26. The absorption spectrum of a dye is shown below. Which wavelength listed has the greatest transmission? So the higher up it is, this is the most absorbed. The lower it is, this is the most transmitted. Which means 360 is the most transmitted. Okay. And if the question said, what color would this appear? Do we see the colors that are absorbed by a sample? No, they never make it to our eyes. So we see the colors that are transmitted. 360 is technically, or is actually ultraviolet, so we wouldn't see this. But if you're ever asked what color you see, it's the complementary color of the most absorbed color, which in this case, 471, there's a color wheel on your data sheet. I think 471 corresponds to blue. So this would absorb blue and appear the complementary color, which is orange. 27, which of the following statements about effective nuclear charge ZEFF is false? All right, let's go through these. The effective nuclear charge of a 2p orbital is greater than that for a 2s orbital in the same atom or ion. So for any given shell, let's just say n equals 4. For s versus 4p versus 4d versus 4f, 4s is always closest to the nucleus. And so this is going to have, let's see, the effective nuclear charge. So S is always going to experience a greater effective nuclear charge than the P, which will experience a greater effective nuclear charge than the D, which will experience a greater effective nuclear charge than the F. Okay. So in terms of these, it says the effective nuclear charge of a 2p orbital is greater than a 2s orbital in the same atom or ion. That is false. 2s is always going to be greater. So this one is false. But then just to address the other ones here, a moment. Oh no. Effective nuclear charge of any orbital in an atom depends on both the number of protons and electrons. That's true. The more protons, the greater it's going to be. The more electrons, the more shielding there is. C, use of effective nuclear charge provides an approximate way of accounting for the effects of electron-electron repulsion. That's true. The more electrons there are, the more shielding there is. And the shielding is accounted for in the equation, which is effective nuclear charge is equal to Z, the number of protons, minus S, the number of shielding electrons. And then effective nuclear charge is 2 for a 1s orbital on helium plus. Helium has 2 protons, and S would be equal to 0. There's no shielding electrons if there's only 1 electron. 2 minus 0 is 2. That one's also true. All right, 28. A spectrophotometer is used to measure the absorbance of a sample. The maximum absorption is found to correspond to 3.26 times 10 to the negative 19th joules per photon. What color would this sample appear to the eye? All right. Oh, here's our color wheel. So, okay. To answer a problem like this, we need to find wavelength. On your data table are 2 equations that relate energy and wavelength. The first is energy is equal to Planck's constant times nu, the frequency. The other one is the speed of light is equal to lambda, the wavelength of a photon, times frequency. Honestly, there's a more useful, generally speaking, form of these equations if we combine them together. It's not on your data table. You don't technically need it, but it's pretty useful. If we combine these two, and I apologize in advance, this one's pretty awful. How many of you are familiar with the beverage high C? I see like fruit punch. Yeah, all right. So we have high C. Have you ever seen what happens if you put it over a lamb? You take that fruit punch and you pour it over a lamb. Do you think the lamb's going to like that with its wool coat? A fruit punch all over it? No, they get energetic. Ooh. E equals HC over lambda, high C over a lamb. It's really, really dumb, but it works. Anecdotally, last fall, I had somebody come into the resource room and say, I'm a senior, high C over a lamb. And I was delighted to hear that. Anyway, some of the, use it if you want. Yeah. But what this does is it relates energy and wavelength. So energy, check, wavelength, check. And the energy is in joules per photon. If you're given kilojoules per mole, you have to convert to joules per photon before using this equation. Here, we're given the energy in joules per photon, so we're good to go. So what I'm going to do is plug all this in. 3.26 times 10 to the negative 9th joules is equal to Planck's constant is 6.63 times 10 to the negative 34th joule seconds. The speed of light is 3 times 10 to the 8th meters per second. And then lambda is what we're solving for. I'm going to multiply both sides by lambda, which will cancel out lambda here. And then once we do that, I'm going to divide both sides by the 3.26 times 10 to the negative 19th joules. When we do, joules cancels out, seconds cancels out, and we're left with just meters. In this case, it ends up equaling 610. Lambda equals 600 and, excuse me, what will actually appear on your calculator is 6.10 times 10 to the negative 7th meters. The visible spectrum is usually reported in nanometers. 1 nanometer. So if you have 6.10 times 10 to the negative 7th meters, for every 1 nanometer, there's 1 times 10 to the negative 9th meters. So this equals 610. The other way that you can go about doing this is if you move this decimal over 2, it equals 610 times 10 to the negative 9th. Meters times 10 to the negative 9th means nano. So there's a few right ways you can go about doing this. The other thing that I do want to point out, the visible spectrum is always on the order of hundreds of nanometers. Okay, a little idiosyncrasy with calculators. When you do this calculation, what you'll end up getting sorry, I just want to share this because this comes up pretty frequently. Okay. When doing this calculation, enhance, 6.63 times 10 to the negative 34th times 3 times 10 to the 8th divided by our lambda, or excuse me, our energy, 3.26 times 10 to the negative 19th. If you use floating point notation on your calculator, you might get an answer that looks like this, 0.00000061, okay? In order to change a number like this that gets cut off, if you go to psi, it'll turn it into scientific notation. And the other reason why I want to point that out is if you ever have anything on order of 10 to the negative 9th, it will cut off everything except for the last digit. And this way you can see to be more precise. Okay, it's just something common that comes up, so I wanted to address that. Okay. And we're back. All right, 2 more problems. Which of the following is not a correct statement related to the regulation of Earth's temperature? This one's a little wordy. The sun's emission is well represented by the spectrum of a thermal black body radiator. This is true. Black body radiators are bodies that give off a spectrum of different wavelengths. This is true. Earth, like the sun, radiates energy. The main difference is that the Earth's radiation is much weaker. That's true, thankfully for us, and mostly at an infrared and longer wavelengths. So this one is also true. Lower energy is being emitted from the Earth. In the absence of an atmosphere, the average temperature of the Earth would be well below the freezing point of water. This is also true. The greenhouse effect is what prevents us from being an ice planet. Water molecules trapping in heat keeps the troposphere warm at night. If you think about what happens at a desert, most deserts are really hot during the day when the sun shines down, but then at night, the temperatures plummet because there's nothing there to hold in the heat in the atmosphere. So C is also true. D says gases like water, carbon dioxide, and methane transmit visible light, but trap infrared light, much like glass does in a greenhouse. Variations in the concentrations of these gases, especially CO2, are directly linked to global temperatures. This is also true. Anything with an asymmetric, well, actually, in this particular semester, we talked more about the asymmetric bonds earlier. So this is going to be covered more thoroughly later. We make sure that the exams cover the things that we actually talk about in a given semester. So just want to address this variance. Anyway, this is also true. Water, carbon dioxide, and methane are all greenhouse gases. Greenhouse gas means they absorb infrared light, and they translate that infrared light into vibrations, which can then be translated into heat. Which leaves E. All of the above statements are incorrect. And E is also incorrect because all of the above statements are correct. This is a typo. So there is no technical right answer here. The key says E, but we're just gonna change that. Okay. So it was just a typo. And don't worry, all the questions are heavily vetted to make sure they're correct. And if there ever is an incorrect question on the exam, it's thrown out and everybody gets credit for it. Okay. Okay. So then we have 3 more questions. Your exam is 30 questions. They were 32 during the semester. They're 30 now. When a photon with energy sufficient to overcome electron binding energy strikes the metal surface, the electron can be ejected from the metal, and any excess energy is converted into the kinetic energy of the ejected electron. Both blue and green light eject electrons. Which one has a higher kinetic energy? This is a very wordy way of asking which of these photons is higher in energy. Okay. And to address that, let's actually put together the electromagnetic spectrum, because it seems like a lot, but what I hope you'll see is the electromagnetic spectrum, actually ordering it isn't terrible. Can anybody tell me a mnemonic for the visible spectrum? Like if you see a rainbow, it's yes, Roy G. Biv, or Vib G. Yor. So red, orange, yellow, green, blue, indigo, violet. Just like that, in the words of John Bon Jovi, whoa, we're 7/13 of the way there. We actually have about half of the electromagnetic spectrum done already. The next 2 we can fill in quite nicely. If we go beyond violet, you're not just looking at regular violet, you're looking at ultraviolet. So after violet is UV, ultraviolet. If you go beyond red, you're not looking at regular red, you're looking at infrared. Now then, to finish off the spectrum, there's 2 more on each side. The way that I like to remember which side corresponds to high energy versus low energy is if you walk outside on a bright sunny day without any skin protection on, you're just going to stand there for 12 hours. What type of electromagnetic radiation is it that will wreak havoc on skin cells? Ultraviolet. The reason why it does it is because it's really high energy. It can break bonds. So this side is higher in energy, which means shorter wavelength. Long waves are low energy, short waves are high energy. This side corresponds to lower energy, which means longer wavelength. Going beyond violet, there's a type of radiation frequently used in medical imaging that is so high in energy that usually the people who work with it all day stand behind lead to protect themselves from constant exposure. What type of rays are those? X-rays. So X-rays are higher in energy. And then the highest energy radiation of them all sounds like something from a Marvel comic book. What type of radiation is the highest energy? Gamma. Also, fun fact about Marvel comic books and gamma radiation. Famous alumni from Penn State, Bruce Banner, the Hulk, took graduate work in the Penn State physics department, canonically. Sorry. Infrared. If we go past infrared, the two types of radiation there are microwaves. Microwaves are relatively low in energy, but they resonate with water. So water absorbs them, and the translation of energy is why microwaves can heat our food. And the lowest energy of them all is radio. The only two we actually need to answer this question are green versus blue. But I just want to go through this all, because it's sometimes useful to put them in order. So the higher energy one is blue. Blue light yields electrons with higher kinetic energy. Greater energy kicks electrons off more quickly. 31. This is a problem that oftentimes causes a lot of consternation in the homework. We've got this made-up system of different energy levels, and the question is how many emission lines would be observed for the system? Emission means we're going from higher energy to lower energy, first of all. And any given energy corresponds to an emission. But what makes this one challenging the first time you go through it, but not the second time, is if we look at this energy gap here from 4 to 3, we're told that this corresponds to half a Rydberg. The common mistake that's made is then saying, okay, that's one emission, this is a second emission from 3 to 2. But it's not. They both correspond to the same energy, which means they're the same exact wavelength of light. So they would produce the same emission line. So far, we only have one, half a Rydberg. But there's more combinations we can have. Like, for example, if we go from 4 to 3, or excuse me, 4 to 2, this is one full Rydberg, 1/2 plus 1/2. If we go from 2 to 1, this is also one Rydberg. So this would also create one unique line. If we go from 3 down to 1, this is a unique emission. It would be 1.5 Rydbergs. And then finally, if we go from 4 to 1, that would also be a unique emission. So there are 4 unique emission lines. So when you know how to do these problems, they're actually kind of fun. You just look for how many unique incremental changes there are. And we're done. Okay? Which leads us to the last problem. The Bohr model for a one-electron system, the energy of the nth orbit is given by the following equation, where Z is the nuclear charge. If the ionization energy of the ground state of hydrogen atom is 1,310 kilojoules per mole, what is the expected ionization energy of the ground state of helium plus? Really convoluted, but there's 2 ways of doing this problem, the longer way and then a fast way. I'm going to do the longer way first. We can use this equation here to give the energy per atom. So the energy of, it's in the first orbit, is equal to negative 2.18 times 10 to the negative 18th joules Helium is element number 2, which means Z is equal to 2. And N in the ground state is going to be N equals 1. It's the lowest energy level. So all of this together ends up giving us 8 negative 8.72 times 10 to the negative 18th joules, and that's per electron. This question wants to know kilojoules per mole, so we have to do some calculations. For every 1 kilojoule, there are 1,000 joules. And then for every 1 mole, there are 6.02 times 10 to the 23rd electrons. So this ends up equaling E. End up getting 5,249 kilojoules per mole. That's one way of doing it. The other way that you can do it is it tells us the ionization energy of hydrogen. Hydrogen C equals 1, which means looking at this equation, everything else here, this and this would both be the same for helium plus. The only thing that would change is Z. So instead of 1 squared, it would be 2 squared, which is 4, meaning the energy would be 4 times greater. So you can take this number and multiply it by 4 and get the same answer, is the quick way of going about this. Okay? And that is practice exam 1C. Again, I can tell you that a lot of these types of questions are represented on the actual exam itself. How did you feel? Like, how are we feeling? Okay. So what I recommend doing is, since we've gone through this one, at some point in the next few days, take exam 1A as a practice exam. See how you do. The stuff that you're getting and flying through, don't worry about going back to those. Look at the stuff that you're not getting and that you want to work on a little bit, then take 1B. There are reviews all throughout the weekend. There are copious office hours, but keep up the great work. Dominate that first exam, and thank you all for your time. Thanks for coming out tonight. My pleasure.